Alright everyone, this is part 2 of lecture 7. So let's continue talking about continuity. So a function f is continuous on an interval if it is continuous at every point on that interval. Let's consider the following graphs. Go number 1 and 2. Let's say we have the interval a to b, and we have a function that looks like this. So this is the interval AB, and then the other graph, let's call this one 2, will be the following. Still in an interval A to B. Now we have it that A is not included on the interval, it's the endpoint, but B is. Alright, so these functions, we can see both of these functions are continuous for all x's in the interval A and B, the open interval. We can see that both 1 and 2 are continuous on the interval AB. This is an open interval, so keep that in mind. This is an open interval. And we could see, so that interval is basically from here to here on both of them, not including A and B. So if you were to pick up a value, let's call that value xi, then that value, no matter where you pick within that interval, is going to have an output f of xi. It doesn't matter where you choose the xi to be. If it is within this interval AB, then you'll be able to always find the output on the function. So both of these are continuous on that open interval A and B. But what about the endpoints? We can see that for the first one, this point right here, f of A, is included in the domain, but f of B is not included in the domain. So these functions, we're going to be talking about something called right continuity, or right continuous and left continuous. So we can actually express continuity in terms of the left and the right, much like we did with limits, where we took left-sided and right-sided limits. We will be able to do the same. So let me define something right now. So a function f is continuous from the right, and we call this right continuous. At A, if the limit as x goes to A from the right of f of x is equal to f of A. And similarly, f is continuous from the left, and this is aptly named left continuous, if the limit as x goes to A from the left side now is equal to f of A. So this looks almost identical to the definition of continuity, but now we are looking at the limit from the left and to the from the right, and it should be b, f of b. Then I'm missing something. At, so f is continuous at b. From the left. This is important because we have a left point and a right point, so and they're not the same. Now, when you combine both of these definitions, both the left and right side, with the definition of continuity at a point, then we can actually say whether these functions 1 and 2 are actually continuous or not. We already said that these functions are continuous between the open interval a and b. Well, we can also now see that for graph number 1, if you take the limit as x approaches a from the right, meaning you're going in this direction, then the function values are approaching this particular point. And that particular point is indeed defined in our domain. It's part of our domain, which means that the limit as x approaches a from the right is the same thing as f of a. If you were to take the limit, you will get this point, but that point is precisely the point that we get when you plug in a into the function. And the same is true for this one right here if you go from the left side. So if you were to take the limit as x approaches b from the left side, you'll be approaching this point right here, but that point is precisely the value of f of b. So f of b is equal to the limit from the left as x goes to b of f of x. This should be a b down here, not a b from the left. Alright, so there's one more definition, and this is a very important definition that will also come into play throughout the course and in other classes that you take as well. So if you continue to study mathematics, especially as you move into analysis, this notion of continuity will become very important. So a function f is continuous on an interval I here stands for interval, so that's how you remember it, if it is continuous at all points of I. If I contains endpoints, then continuity on I means continuous from the right or left at the endpoints. And this is pretty useful for us. So for example, if you're given the following function, let's say it's a piecewise defined function, let's say this is an open hole right here, it goes up like this, and then this is actually included, and this goes up like this, then we can tell whether this is continuous or not on the interval of definition. So these functions are both going to infinity as they go to positive infinity and negative infinity on the x-axis. So if we notice, if you approach the origin from the right side, then the function values are approaching 0 from the right. And if you approach it from the left, not approaching 0, if you approach from the right, you're approaching this value here, which I didn't give it a number, let's call it 4. So you're approaching 4. but 4 is not included. But so it is not right continuous because the 4 is not included, but it will be left continuous because this point right here, which we call 1, is actually included. So this is left continuous since limit as x goes to 0 from the left of f of x equals f of f of 0. So this is definitely left continuous. Now you could do this for any function. You could check whether they're going to be left or right continuous or just continuous altogether. So for example, if you had a function that now looked like this, you know, you go down here and then, you know, it goes like this, and this will actually be a continuous function. It will be right continuous. I began on this side, but it will not be left continuous because we still have that discontinuity. Alright, so that is left and right continuity and continuity on an interval. Being continuous on an interval, once again, is extremely important because the understanding when you're continuous will help you solve problems, and you will make some theorems hold true, and we may see that at the end of this video. One of those very important theorems that we will use during the semester assumes that the function is continuous on the interval that we're working with. All right, so let's move into functions that involve roots. We have seen so far the scenarios of polynomial functions and rational functions. Thanks to the left and right sided continuity, we can now also work with piecewise defined functions. However, we have yet to speak about rational functions, radical functions. Apologies, radical functions. These are functions that involve radicals. Kind of left that vague up there. Alright, so if you remember from the limit laws that I had written down in the previous lecture, I believe it was limit law number 7, the last one. We had that the limit as x goes to a of f of x to the power 1 over n is equal to the limit as x goes to a of f of x raised to the power 1 over n. So what this means is that we could first take the limit, then raise it to the fractional power, meaning we could take the root after we take the limit. And we just saw that in the last example that we did in part 1 of this lecture. But this is provided, this only holds if f of x is positive for x's near a and n being even. Because remember, we cannot have negative inside of even roots. Now, if n is odd, if n is an odd number, and the function that we're working with is continuous, then the function f of x to the power 1 over n is continuous at a because of the following. Because the limit as x goes to a of f of x to the power 1 over n is the same thing as the limit as x goes to a of f of x to the power 1 over n. So now we're taking the limit first, but we just said that n is odd. We know that f is continuous, and when we take the limit of a continuous function, so we know that this is continuous at a point because we just set it up here. This is continuous. And from continuity, from part 1 in this video, we know that when a function is continuous at a point a, then it is the same thing as simply plugging in a for x. So it's the same thing as just doing f of a. And then we just have to raise it to the power 1 over n. So this inner portion we get because f is continuous. This allows us to simply use direct substitution to solve the limit problem. And then once we have that value, we simply take the nth root of that, and we will have a solution. Now when n is even, we have difficulties. When n is an even number, we have to be more careful. And the reason for that is, remember that the square root of -1 is an imaginary number. And in this class, we are not dealing with imaginary numbers, so the domain of f of x equals square root of x in this class is x being greater than or equal to 0. But if we are dealing with an even root, all even roots have to be positive. The same is not the case for cubic roots or odd roots. Odd roots do not have to be, you could have negative numbers inside of an odd root. That is okay. But that's not the case with even roots. If you don't remember this, then I suggest reviewing some college algebra, because this will come in handy. Alright? Well, what happens when n is even? When n is even, then, excuse me, if n is even, then f of x to the 1 over n is continuous at all points of a at which f is continuous. And the output values of the function are all positive. So if you have an even root, then that function is going to be continuous whenever f itself is continuous and the values of the outputs are positive. Okay, so let's do an example of that to see what we mean. Let's say we're working with f of x equals 9 minus x squared. Okay, so this is an even root. So by this theorem, we know that this is going to be continuous at all points for which of which f is continuous and f of a is positive. So we cannot have any output values being negative. So now, if we notice, if we try to graph this, this is the same thing as y equals square root of 9 minus x squared. And if you wanted to solve this, one way of noticing what's going on is to square both sides. That will get rid of the square root, so you'll be left with 9 minus x squared. And then if you move the x over, if you add x on both sides, you get y squared plus x squared equals 9. But you know from pre-calculus that this is the graph of a circle of radius 3. This represents the graph of a circle of radius 3. And when we move the x over, and then we take the square root, we actually take the positive and negative square root. And the one that we're working with is the positive one. So that means that we are actually just working with the upper half circle. And this bottom one is not part of our function. So we're only working with the top one. So this is what our function looks like, the thing in red. And this 3, just assume that it's here. Alright? So we can clearly see that this is going to be continuous. And the endpoints are included. But we still have to say a little bit more about this. So we can see that we are going to be continuous at every point within the domain. What is the domain? Well, what is the highest value that x takes and the lowest value that x takes? Clearly from the picture we know that that's going to be 3 minus 3 to 3, and they're included, because if you plug in negative 3 into this function, then what do you get? You get 9 minus 9, which is 0, so that's included. And if you just plug positive 3, you're also going to get 0, so that's also included. And now, if you were to take the limit, for example, just to really verify the endpoints, if you were to take the limit as x goes to 3 from the left side of f of x, then that'll be the same thing as taking the limit as x goes to 3 from the left side of 9 minus x squared. But once again, we just figure out what 9 minus x squared is when you plug in 3. And we could just plug in 3 because this is a continuous function. And all these values are positive, so we could simply just plug in. But we already know that that's going to be 0, so both the value of the function and the limit are 0. Now, the same thing is going to be true when you try to find the limit as x goes to minus 3 from the right side at f of x. The same type of computation. And again, because we are continuous at all of those points, then we can simply just use the plug-in method, and we will see that it's going to be 0. So because the limit equals the output value, then we know that we have continuity at both of them. Now, since f of x is continuous at the endpoints, and it is also continuous on the interval minus 3 to 3, this means that f of x is continuous on the interval negative 3 to 3 with the endpoints included. Therefore, f is continuous. you could simply say f is continuous, because it is continuous at the endpoint. It is continuous at every point in its on the interval, so it is continuous. Now let's do just one more example. Let's say you're given the function g of x equals x squared minus 2x plus 4 raised to the power 2/3. Well, if you wanted to figure out whether this continues, then you should first again realize that we're dealing with a composition of a function. So, and we already know that the composition of functions is continuous. So we could say, use a different name, f of x is simply the polynomial x squared minus 2x plus 4. And this is continuous because we know that polynomial functions are all continuous. This is continuous, so that's a good thing. Let's say h of x is going to be the cubic root x squared of x squared. So because since h of x involves an odd root, then by the fact given before, this is also continuous. And we get this one for free because we already explained how that is. This is a fact. So where is it? Right up here. If n is an odd number and f is continuous, then this is going to be continuous. So let me just make h of x a little bit clearer so you can see why this is the case. X to the 2/3 is the same thing as x squared to the power 1/3. X squared we know is continuous, that's just a parabola. So f, if we call this, I guess f, I already used f, let's call it k. So the inner function is continuous. So the function raised to the root, to an odd root, is also going to be continuous by the fact given above. So that means that this is also continuous. And the composition of continuous functions we saw in part 1 of this lecture is also continuous. Okay, so if we are continuous at that point, then we're continuous in the composition. All right, so that's pretty good. I'm gonna do another example just so maybe we could drive that home. So let's say f of x is now equal to x cubed minus 3x plus 4. This raised to the power 3/5. Once again, the inner function I'll call g of x is x cubed minus 3x plus 4. This is continuous because it is a polynomial. The outer function I'll call k of x is x to the 3/5, which is the same thing as x cubed to the power 1/5. This is by the rules of exponents. So the rules of exponents says that if you have a to the power x and you're multiplying that by y, and that is the same thing as a to the x times y. And remember, 3/5 is the same thing as 1/5 times 3/1, or simply times 3. So I'm simply just rewriting this. And we know that x cubed is continuous because it's a polynomial. And by the fact given above, since this is being raised to an odd power, here n is 5 and 5 is odd, then that's also continuous. So f of x must also be continuous, since f of x is the same thing as k k composed with g. This is the composition of k with g, and both k and g are continuous. So f of x is continuous for all x's. Alright, so that's continuity for radical functions, for roots. Now we have a little bit more of a trickier situation when we begin to consider more difficult functions, and that is the continuity of transcendental functions. Okay, so a transcendental function is a function that's not algebraic. Some of them include sine, cosine, tangent. Those will be transcendental functions, right? So we saw that the limit as x goes to 0 of sine of x was equal to 0 by the squeeze theorem. We proved this. Earlier in, I believe, lecture 5. And we also showed that the limit as x goes to 0 of cosine of x was equal to 1, also by using the squeeze theorem. Alright, so what about sine and cosine? Are sine and cosine continuous? Well, we know that you could use a calculator to verify this, or the sine and cosine waves. We know that sine of 0 is simply equal to 0, and cosine of 0 is equal to 1. And this we know from their waves. So the sine wave looks like this. It is 0 at 0, so 2 pi, and so this is sine x. And the cosine wave begins at 1, goes on to minus 1, and also ends at 2 pi. So this will be y equals cosine of x. Right? Well, notice this. Notice that the limit as x goes to 0 of sine of x equals 0. We said that up here, right? But that is the same thing as sine of 0 when you plug in 0. So this means that sine is continuous at x equals 0. So sine is continuous at actually all points. In its domain, because it goes forever, both in the negative direction and the positive direction. There are no issues. The only issue that we could have gotten was at 0, and we clearly see that there is no issue. Similarly, for cosine, we have that is equal to 0, but that's the same, not to 0, to 1, but that is the same thing as cosine of 0. So cosine of x is continuous also at x equals 0 and all other x's. In its domain. So both sine and cosine are continuous on the interval minus infinity to infinity. And this is actually a very nice and useful thing to know. It turns out that all the other trigonometric functions are also continuous on their domain. So it turns out that all other trigonometric functions are continuous in their domain. So we don't have to worry about them not being continuous. Alright? Now, what about the exponential functions? Are they continuous? Well, if you remember the graph of e to the x, and the graph of e to the x looks kind of like this. At 0 you get 1, and it grows very quickly. That also is how the graph of b to the x looks like as well. It looks very similar. It's also, this is a y, b to the x. This is also an exponential function. Well, it turns out that the continuity of exponential functions of the form y equals b to the x, where b is bigger than 0 and less than 1, or b is bigger than 1, is continuous. Right, so both of these are continuous. Now, this is going to be a little bit trickier, and we will not actually be able to prove this in this class. But x here, this x that we use as an exponent, for this class I'm going to assume that it's a fraction of the form a over b, where b is not equal to 0, or it's an integer or a constant. Now, it actually gets very tricky to show that exponential functions that are raised to a irrational number are continuous. For example, what if somebody gives you y equals say square root of 2 to the square root of 2? It's a perfectly fine value, but what does that actually mean? You know, how do you compute something like this? And we will not see how to compute something like this by hand until we go into Calculus 2 class. So we will not delve too much in this class. Now, it also turns out that the reflection and the inverse, rather, the inverse of functions is continuous, with a few caveats. So, for example, if somebody gave you something like this, y equals x cubed, then its inverse is also going to be continuous, because x cubed is continuous. Or if somebody gave you f of x equals sine of x, then its inverse, cosecant of x, is also continuous. Okay, so this is also very useful. Right, so let me just write that as a theorem. I will not prove it, but I'll write it. If a function f is continuous on an interval I and has an inverse on I, then its inverse, denoted by f inverse, is also continuous. and this is on the interval containing the points of f of x where x is in the interval I. Okay, so now we know that if you are given a function that is continuous at all points, then its inverse is also going to be continuous on that interval. So for example, you may have a function like this. Let's say you have a function that looks like this. This is clearly not continuous, clearly, because we have a jump here. But if you were to, look at this interval, just a to b, then this function from a to b does have an inverse. This continuous here. So it does have an inverse. This 1 to 1 is onto, so it has an inverse. Well, the inverse of this function on this interval is also going to be continuous. So if you were, let's just assume that the inverse is somewhere here. Then on that interval from a to b, that function is going to be continuous. Now I just said that all of the trigonometric functions are continuous. Let me just list all of the functions that are actually continuous, all of the transcendental functions that are continuous. So the following functions are all continuous. Right? So what are they? Well, the trigonometric functions are all continuous. So sine of x is continuous, cosine of x is continuous, tangent of x is continuous, that's just sine over cosine, and this is on their domain. So let me just put here on their domain, because if you remember, tangent is sine over cosine, so whenever cosine is 0, you have a discontinuity, you have a vertical asymptote. So the domain of tangent is pi over 2 minus pi over 2 to pi over 2. So what else? Cotangent of x is continuous, secant of x is continuous, cosecant of x is also continuous. The inverse of these functions on their domain is continuous, so sine inverse is continuous, cosine inverse is continuous, tangent inverse is continuous, cotangent inverse is continuous. Cotangent, secant, the inverse of secant is continuous, and the inverse of cosecant is continuous. And also the following exponentials are continuous as well. So b to the x is continuous, e to the x is continuous, and the logarithm log b of x and ln of x are also continuous functions. So all of these are continuous on their respective domains. Now I'm going to do one example of how you will go about determining whether our function is continuous or not. And it's going to be with using one of these trigonometric functions. So let's say we're taking the limit as x goes to 0 of cosine square x minus 1 divided by cosine of x minus 1. Now please do not please do not go ahead and cancel out, because these are two different expressions. This is a cosine square of x minus 1, and in the denominator we have cosine of x minus 1. They're completely different, so you cannot just cancel them out. I see students who begin to do cancellation because they look alike, and they just leave cosine of x on the top. That is what we call wrong, so please don't do that. What you should realize here, though, is that The graph of cosine, especially for the denominator, the graph of cosine of x looks like this, kinda. It's a very rough sketch. And at 0 we know we have 1. Right? Now we are concerned about the denominator of this function being 0. Why? Because when the denominator is equal to 0, we have that the function is undefined. So for that reason, we cannot simply plug in x equals 0 here. We cannot just plug in, because if you plug in into the denominator, you're going to get 1 minus 1, and that's undefined. So we can't just plug in. However, if we look at the numerator as x approaches 0 is always positive. So all of these values are always positive as we approach 0. So they're actually not 0 themselves. And cosine of x by itself is also not 0. Cosine of x is just 1. And using that fact, let's see. So note, cosine of x as x goes to 0 is not 0. So I'm going to use that fact right now to simplify and cancel. So I could actually simplify this. I could do the limit as x goes to 0 of, notice that this is the difference of two perfect squares, because it's cosine squared minus 1, and 1 is the same thing as 1 squared. So I could say cosine of x minus 1 times cosine of x plus 1. So I'm using the fact that I have the difference of two perfect squares in the numerator to rewrite it. And now, because of what I just wrote here, I'm allowed to cancel the cosine of x minus 1 from the denominator with the 1 on the numerator, because cosine of x is not 0 as we approach 0. Yeah. Might need to get a new whiteboard app, because it just keeps on crashing. These take so much time too. Okay. All right, we're back. So long as cosine of x is not 0, I'm allowed to cancel. Okay, so we cancel this out, and we're left with just limit as x goes to 0 of cosine of x plus 1. But this is the same thing as, now I could plug in the 0 here, so this is just cosine of 0 plus 1. But cosine of 0 we know is 1, and 1 plus 1 is 2. So this limit is actually going to be equal to 2. So we have actually found what the limit is. All right. Now the limit exists, so we are good to go. All right. So this is gonna lead us now to a very important theorem in mathematics. It's called the intermediate value theorem. And the intermediate value theorem basically tries to solve a problem that arises in mathematics. So a common theme in any math class is finding the solution or solutions, so there may be more than one, of functions of the form f of x equals L. Right? So we're always looking for what f of x equals. Now, sometimes, in fact most of the time, but sometimes these functions may not have solutions at x. The solutions may not exist. So sometimes these functions may not have a solution. And an example of this is when you attempt to use the quadratic formula on a quadratic that looks like this. Let's say it's center here, this particular point. Let's say this is point 1, 2. Yeah, 1, 2. Right, so we have this particular parabola, and we're trying to find out what the zeros of this parabola are. Well, if you are only given the function of that parabola, then it may actually be very difficult to figure out what the value of the function is. And the reason for that is to find the zeros of the function. The reason for that is because this function will not have any zeros because you're never actually touching the x-axis. So if you were to attempt to use the quadratic formula for this, you will very quickly realize that this does not have a solution. So like if somebody gave you something like this, x squared plus 3x plus 4, and you try to find the zeros of this, you'll have a very difficult time because the solutions of this equation, when you try to solve for the x-intercepts, when you plug in 0 here for y, do not exist in the real numbers. They're imaginary. So it may be useful to actually know that there will not be a solution from the get-go without doing too much work, and that is what the intermediate value theorem helps you do. It gives you a way of actually determining whether the function is going to have a solution on an interval or not. So if you're given a function, call it f, and let's say some number, a constant, call it L, and we will assume L lies strictly between f of a and f of b, then the intermediate value theorem says that if f is continuous, on the interval AB, then the graph of f must cross the line y equals L at some point on that interval. At some, let's call it C value on the interval AB. So let me just draw a picture of what I'm saying here so you have an idea. So let's say you have a function. This is a continuous function. It has a value here, f of a. It has some value here. Let's call it f of b. And we are saying that there's a constant L. That constant is between f of a and f of b, as we set up here. So f lies strictly between f of a and f of b. So that means that, let's say, L is somewhere here. So L is this blue line. That is what L is. And that says that if f is continuous, then f is going to have to cross this line at some point, and that point we'll call it c. Okay, so that just means that we could find a value for c such that that value is equal to L. So if we connected these two endpoints, then we will see that somewhere here this c value is going to have exactly the output that will be equivalent to L. And this only happens if the function f is continuous. If f is not continuous, then this is not the case. So for example, if f was not continuous, then we could have something like this. So let's say we have A, we have B, and then we have L. But now, because this is not continuous, we could have something that looks like this. Just B. And now the line L does not get touched by any value of C, because for this C, the value is up here. That's what f of c will be. This f of b is a little bit low. So f of c will be somewhere here instead of being exactly L. So that's why we need the function to be continuous for this to hold. If the function is not continuous, then the theorem doesn't actually work. So continuity, we can now see, is playing a very important role in theorems that we are coming across. So let me actually just tell you the theorem, and that will be the end of the section on continuity. So the intermediate values theorem says the following. It says suppose f is continuous on the interval AB, and L is a number strictly between f of A and f of B, then there exists at least one number C in the interval AB satisfying f of c is equal to L. So this is actually very useful when you're considering a function. Like, let's say somebody tells you, let's say somebody gives you the following. Somebody tells you that the function has at 5, f of 5 is equal to 25. So this is a 0.525. And then they also tell you that at -2, and this is not to scale, at -2 the function is -2 -8, and again not to scale. Then if somebody asked you, they only gave you this information, if somebody asked you whether this function has any x-intercepts, and they tell you the function is continuous, so you're told that the function is continuous, and you're given these 2 points, then you know that the function is definitely going to have to cross the x-axis at least once. Why? Because it is continuous. So let's say if you go, you need to get from this point to that point up there. So let's say you go up here, eventually you're going to have to cross the axis, because there's no way for you to get up here without crossing the axis if f is continuous, and we are saying it is. So you're going to have to connect it somehow, and it doesn't matter where you connect it, it's going to be continuous at the point. It's going to be continuous at every point, so you're going to have at least at least one x-intercept. Now, you could have more than one. You could have some function that does something like this. And that's okay. Here we have multiple ones. But because f is continuous and you know that you have a point on the negative side and a point on the positive side, you are guaranteed to have at least one solution for the series of the function. For another example would be if somebody told you that you have this interval, so you have a being on the negative side, b being on the positive side, and then you are told that the function is continuous, and you're given a value here. Let's say this is here, and let's say b is up here, right? And you're given this point c in here, and you're asked to find whether c is a solution to this function. If the function is continuous, then c is definitely a solution, because you eventually are going to touch the value that c gets assigned to. That will be somewhere here. That's only because we know that the function is continuous. So continuity will definitely be playing a big role as we move along, especially when we get to the so-called derivative. Okay? Especially when we get to the derivative. In any case, that is all for lecture number 7. If you have any feedback on this lecture so far, please send me an email. Make sure you are completing all of your assignments. Thank you for your time.